And now in this lecture we'll answer two questions. In the first question we'll find out the area of this big circle, and in the second question we'll find out the area of this rectangle ABCD using two different methods. So we start with the first question. In the drawing we have two circles that touch each other at this point C. In addition, you know that this is line segment AC that is equal to 6 units in its length. This is line segment CB that is equal to 9 units in its length. This is tangent DE that is tangent to this small circle at point B. And tangent DE is also tangent to this big circle at this point. So when you find the point of tendency of tangent DE with this big circle, this point is point M. This is point B that, and it is considered as an external point in relation to this big circle. So for this common external point B, we have tangent BM that is tangent to this big circle at point M. In addition, from the same common external point B, if we draw this straight line, it will cut the big circle at 2 points, points A and point C. So in this way we created here called AC. So therefore here we can implement rule 10. So I'll press quickly rule 10. According to rule 10, we have in the domain a circle, and from this common external point B, we have here tangent PT that is tangent to this circle at point T. In addition, from the same common external point P, we have here chord AB. If we draw a straight line from point P, it will cut the circle at 2 points, point A and point B. This way we created here chord AB. So in this drawing, according to this rule 10, the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. We can definitely implement rule 10 in our drawing. Why? Because in our drawing, for this common external point B, we have tangent BM that is tangent to this big circle at point M. In addition, from the same common external point B, if we draw this straight line, it will cut the big circle at 2 points, point C and point A. In this way, we already called AC. So all the requirements of rule 10 are satisfied, and therefore according to rule 10, the following equation is true, that BM square equals to BC times BA. Again, BM square equals to BC times BA. So I write it down. So BM square equals to BC times BA. Okay, again, according to rule 10, if we focus on the common external point B, the following equation is true, that BM square equals to BC times BA. BM is the missing tangent, so we leave it as it is, so it is BM square. That is equal to BC. BC is 9 times BA. BA in total is 9 plus 16, that is 25. So according to rule 10, the following equation is true, that BM square equals to BC, that is 9 times BA, that is 25. So in total BM square equals to 9 times 25. Here we take a root out of this equation and we get that BM equals to the square root of 9, that is 3, times the square root of 25, that is 5. So BM in total equals to 3 times 5, that is 15. So the ref of tangent BM is 15 units. So this is tangent BM that is equal to 15 units in its length. In the next step, we'll do a construction. That is to say, from this point C, we draw two tangents to both circles. Actually, we draw a common tangent to both circles. And we define the touching point of the common tangent with tangent DE. This point is point N. Actually, the common tangent CN is tangent to both circles. The common tangent CN is tangent to this small circle at point C, and it is also tangent to this big circle at the same point C. So CN is a common tangent that belongs to both circles. So in the next step, we'll focus on this common example point N. From this common example point N, we have two tangents to this small circle, tangent NB and tangent NC, and according to all two, they are equal to each other. That is to say, NB equals to NC according to all two. So I'll repeat quickly on all two. According to all two, the lengths of two tangents for a common example point to a circle are equal. So in the common circle, this is the common example point P. From this common example point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this all two, they are equal to each other. That is to say, PA equals to PB. So we have already implemented all two in our drawing. In our drawing, from this common example point N, we have two tangents to this small circle, tangent NB and tangent NC. And according to all two, they are equal to each other. That is to say, NB equals to NC. In the next step, I copy triangle CNB, this triangle in a new page, and we will analyze this triangle CNB. So actually, this is angle CNB that I call it from the original drawing. Side CN equals to side NB according to all two. And we have the rule that states that in front of equal sides in the triangle there are equal angles. So in front of this side CN, we have this angle that is actually angle CBN. In front of this side NB, we have this angle that is actually angle NCB. And because of the fact that those two angles are both located in front of those two equal sides, they must be also equal to each other in their sizes. So if we define the size of this angle as alpha, then this angle must be also equal to alpha according to the rule that I mentioned. So in total, we found out that angle NCB equals to alpha and angle CBN also equals to alpha. So this is angle NCB that is equal to alpha, and angle CBN is also equals to alpha. In the next step, we join point C and M together by straight line. and we'll continue to focus on this common sum point N. From this common sum point N, we have two tangents to this big circle, tangent NC and tangent NM. And according to rule 2, they are equal to each other. That is to say, NC equals to NM. So in the next step, we'll copy triangle CNM in Olympiad and we'll analyze this triangle CNM. So actually this is triangle CNM that I copied from the original drawing. In this triangle CNM, side CN equals to side NM according to rule 2. In front of this side CN, we have this angle that is actually angle CMN, and in front of this side MN, we have this angle that is actually angle MCN. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other according to the rule that I mentioned. So in total, if we found out that angle MCN equals to beta and angle CMN also equals to beta. So okay, this is angle MCN that is equal to beta. This is angle CMN that is also equals to beta. In the next step, I'll copy the big triangle MCB in a new page and we'll analyze this big triangle MCB. So actually, this is the big triangle CMB that I copied from the original drawing. We know that the sum of the angles in any triangle is equal to 180 degrees, and especially the sum of the angles in this triangle CMB must be equal to 180 degrees. So which angles we have in the triangle CMB? We have this angle that is alpha, plus this angle that is beta, plus this big angle that is beta plus alpha. In total, the sum of those three angles must be equal to 180 degrees according to the rule that I mentioned. So in this side of the equation, we have alpha plus alpha that is 2 alpha, beta plus beta is 2 beta. So in total, we found out that 2 alpha plus 2 beta equals to 180 degrees. Here we divide this equation by 2, and finally we get that alpha plus beta equals to 180 degrees over 2 is 90 degrees. So if we found out that the size of the big angle MCB is equal to 90 degrees in its size, so angle MCB is the right angle. This is angle MCB, that is the right angle according to what we already found out. So angle MCB is the right angle. angle MCB is a right angle. It is given us the question that AB is a straight line. So if you focus on the left side of the straight line AB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of AB at point C? We have this angle that is the right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we join points A and M together by straight line. By joining points A and M, we can indeed chord AM. Chord AM is a chord in this big circle. And we also, inside this big circle, we have peripheral angle ACM. Peripheral angle ACM is right angle according to rule 3. This is peripheral angle ACM, that is right angle. And according to rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. So I'll take quickly on rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees must subtend on the diameter of the circle. So in the moment we have a circle. This is peripheral angle MAN, and we know that peripheral angle MAN equals to 90 degrees in its size. So it is a right angle. And therefore, according to this rule 5, peripheral angle MAN, that is a right angle, must subtend on the diameter of this circle. And because of the fact that peripheral angle MAN subtends on MN must be the diameter of this circle. So according to rule 5, MN is the diameter of this circle. So any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. So we can definitely implement rule 5 in our drawing. Why? Because in our drawing we have peripheral angle ACM. This is peripheral angle ACM, that is the right angle, and therefore peripheral angle ACM must subtend on the diameter of this big circle. And because of the fact that peripheral angle ACM subtends on AM must be the diameter of this big circle according to rule 5. So I write it down. According to rule 5, chord AM is the diameter of the big circle. And we also know that the center of any circle must be located on the diameter of the circle. Again, the center of any circle must be located on the diameter of the circle. And because of the fact that AM is the diameter of this big circle, the center of this big circle must be located on AM. So this is the center of this big circle. So we define the center of this big circle as O. You can see that point O is definitely located on AM, the diameter of this big circle. So point O is the center of this big circle, point M is the point of the big circle itself, therefore OM is the radius of this big circle. We'll define the radius of this big circle itself, therefore OM equals to R. And because of the fact that the radius OM the radius OM that is equal to R, so the radius OM is drawn to point M, that is the point of tendency of tangent DE with this big circle. And whenever you have a radius that is drawn to the point of tendency, then tangent DE will be perpendicular to the radius MO. If D is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, I'll copy the right big triangle A and B in a new page, and we will implement the Pythagoras theorem on this right big triangle, triangle A and B. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse of the right triangle A and B is AB. AB in total equals to 16 plus 9, that is 25. AM is the missing side, and A and B equals to 15 units in its length, according to rule 10. So actually, this is the right triangle A and B that are according from the original drawing. This right triangle A and B according to the Pythagoras theorem. Here, by PT is the provision for Pythagoras theorem. So according to the Pythagoras theorem, in this right triangle A and B, AB square equals to AM square plus MB square. AB square, that is the square of the hypotenuse, equals to AM square plus MB square. But again, in the right triangle A and B, according to the Pythagoras theorem, AB square equals to AM square plus MB square. AB is 25, therefore AB square is 25 squared, that is 625. And it is equal to AM square. AM is the missing side, so we leave it as it is. So it is AM square plus MB square. MB is 15, therefore MB square is 15 squared, that is 425. So in total, according to the Pythagoras theorem, in the right triangle A and B, 625 equals to AM square plus 225. Here we subtract 225 from this equation, and we get that 625 minus 225 is 400. So 400 equals to AM square. So here we take a root out of this equation, and finally get that AM, the missing side AM, is equal to the square root of 400, that is 20. So the length of the missing side AM is 20 units. But we already found out that according to rule 5, chord AM is the diameter of the big circle. So actually, this is chord AM, that is the diameter of this big circle according to rule 5. So the diameter AM equals to 20. The diameter AM of the big circle equals to 20 units in its length. The diameter is twice as big as the radius. Therefore, the radius must be equal to the diameter divided by 2. So the radius R of this big circle must be equal to the diameter over 2. The diameter AM is 20, and 20 over 2 is 10. So in total we should find out that the radius of the big circle is equal, the radius r equals to 10 units in its length. Our mission is to find out the area of this big circle. So actually we know that the area of any circle is equal to pi times the radius of the circle squared. And therefore the area of this big circle must be equal to pi times the radius of the big circle squared. The radius of the big circle is 10, therefore the radius squared is 10 squared. 10 squared is 100, so in total this expression equals to 100 pi. 100 pi is 314.159 square units. So we found out that the area of this big circle equals to either 100 pi square units, or in terms of numbers it is equal to 314.159 square units. So we finish with the first question. In the next step I will present to you the second question, and we'll solve the second question in two different methods. Our mission in this second question is to find out the area of this rectangle ABCD. So in the moment we have rectangle ABCD and we have this semicircle. Line segment AM equals to 5 minutes in its length. Again, our mission is to find out the area of this rectangle ABCD. So we start with the first method. Because of the fact that ABCD is a rectangle, all those four angles inside this rectangle ABCD are right angles. So okay, this is a right angle. This is also a right angle. This is a right angle. Finally, this is also a right angle. We define the center of this semicircle. This point is point O. We'll define the radius of this semicircle as x. Point O is the center of this semicircle. Point A is the point of the semicircle itself. Therefore, OA is the radius of this semicircle. It is equal to x units in its length according to our definition. We define the point of tendency of this tangent DC with this semicircle. This point is point E. So point O is the center of the semicircle, point E is the point of the semicircle itself, therefore OE is the radius of this semicircle. OE is the radius of this semicircle, that is equal to x units in its length according to our definition. And because of the fact that the radius OE is drawn to point E, that is the point of tendency of tangent DC with this semicircle, and whenever your radius is drawn to the point of tendency, then tangent DC will be perpendicular to the radius EO. If DC is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So inside the small quadrilateral DEOA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 facing angle, in total they must be equal to 360 degrees, according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this 4 facing angle must be equal to 90 degrees in its size. So inside the small quadrilateral DEOA, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this rectangle if not a square. So we will relate to this quadrilateral DEOA is a rectangle because it has 4 right angles. Okay. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle DEOA, side EO must be equal to the opposite side DA. But EO is x, therefore DA must be also equal to x units in its length. In the next step, we define this line segment OB as A, and we define this line segment MB as B. In the next step, we join points O and M together by straight line. What is the definition of line segment OM? Line segment OM starts from point O, that is the center of this semicircle, and ends at point M, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, OM is the radius of this semicircle, that is equal to x units in its length according to our definition. In the next step, I'll copy the right triangle OMB in a new page and we'll implement the Pythagoras theorem on this right triangle OMB. Here by PT is the version for Pythagoras theorem. So actually, this is the right triangle OMB that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle OMB, OM squared equals to MB squared plus BO squared. So I'll write it down. OM squared, that is the square of the hypotenuse, equals to MB squared plus OB squared. The hypotenuse OM is x, therefore OM squared is x squared. And it is equal to MB squared. MB is B, therefore MB squared is B squared plus OB squared. OB is A, therefore OB squared is A squared. So in total, according to equation 1, we should find out that x squared equals to B squared plus A squared. In the next step, I'll copy this right big triangle A and B in the new page and we'll implement the Pythagoras theorem on this right big triangle A and B. Here by PT is a version for Pythagoras theorem. The hypotenuse AM equals to 5 units in its length according to what is given us the question. Side MB equals to B units in its length. And this is side AB, that is equal in total to x plus A. So here, this is the right big triangle A and B that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle A and B, AM squared equals to MB squared plus BA squared. Again, am squared equals to mb squared plus ba squared. So I write it down. This will be equation 2. Am squared, that is the square of the hypotenuse, is equal to mb squared plus ab squared. Am is 5, therefore am squared is 5 squared, that is 25. And it is equal to mb squared. mb is b, therefore mb squared is b squared plus ab squared. ab is x plus a, therefore ab squared is x plus a squared. So in total, according to equation 2, we shall find out that 25 equals to b squared plus x plus a squared. So actually, according to equation 2, we shall find out that 25 equals to b squared plus x plus a squared. X plus a squared equals to x squared plus a squared plus 2 times x times a. Repeat again, according to equation 2, we shall find out that 25 equals to b squared plus x squared plus a squared plus 2xa. So in the right side of this equation 2, we have the expression b squared plus a squared. And we have already found out that according to equation 1, b squared plus a squared equals to x squared. Therefore, we substitute b squared plus a squared in this equation 1 by x squared from equation. We substitute b squared plus a squared in this equation 2 by x squared from this equation 1. We do it now and we get that 25 equals to b squared plus a squared is x squared, and we have x squared again plus 2xa. So in total, according to equation 2, 25 equals to x squared plus x squared is 2x squared plus 2xa. Here we divide this equation 2 by 2 and get that according to equation 2, 25 over 2 is 12.5, and it is equal to 2x squared over 2 is x squared plus 2xa. 2xa over 2 is xa. So in total, according to equation 2, we shall find out that 12.5 equals to x squared plus xa. So according to equation 2, 12.5 equals to x squared plus xa. Here we take out x as a second factor from those two expressions. So x was taken out as a second factor from those two expressions. So what is left from x squared after we took from it x as a second factor? What is left is actually x, and what is left from xa after we took from it x as a common factor? What is left is actually a. So in total, according to equation 2, we shall find out that 12.5 equals to x times x plus a. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. Then again, the area of any rectangle equals to the length of the rectangle times the width. And therefore, the area of rectangle ABCD must be equal to the length of the rectangle ABCD times the width. The length of this rectangle ABCD is AB, and the width is DA. So total the area of rectangle ABCD must be equal to AB times DA. AB in total it is x plus A. DA is x. So in total we should find out that the area of rectangle ABCD equals to AB that is x plus A times DA that is x. So in total the area of rectangle ABCD equals to x plus A times x. But according to this equation 2, x plus A times x equals to 12.5. Therefore, we substitute x plus A times x by 12.5. So in total, we should find out that the area of rectangle ABCD equals to 12.5 square units. So repeat again, the area of this rectangle ABCD is equal to 12.5 square units. So we finish with the first method. In the next step, I will present to you how to find out the area of this rectangle ABCD according to the second method. So first of all, because of the fact that ABCD is a rectangle, all those four angles inside the rectangle ABCD are right angles. So actually, this is a right angle. This is also a right angle. This is a right angle. And this is also a right angle. In the next step, we define the center of this semicircle. This point is point O. And we define the radius of this semicircle as x. OA is the radius of this semicircle, that is x. We've already found out in the first method that dA equals to x. So I'll not repeat on the same explanation. dA equals to x according to the second, dA equals to x according to the first method. In the next step, we define this line segment OB as A, and we define this point as point M. In the next step, we join points M and N together by a straight line. By joining points M and N, we can get the peripheral angle AMN. This is peripheral angle MAN, and this peripheral angle MAN subtend on AN, that is the diameter of this semicircle. And according to rule 7, any peripheral angle that subtend on the diameter of the circle or semicircle must be equal to 90 degrees in its size. And therefore, this peripheral angle AMN that is subtend on AN, that is the diameter of this semicircle, must be equal to 90 degrees in its size according to rule 7. So I repeat quickly on rule 7. According to rule 7, if a peripheral angle subtend on the diameter of the circle, then it is equal to 90 degrees. So in the drawing we have a circle, and we know that AB is the diameter of this circle. In addition, we have here peripheral angle ACN. And because of the fact that peripheral angle ACN subtend on AB, that is the diameter of this circle, peripheral angle ACN must be equal to 90 degrees in its size according to this rule 7. And because of the fact that peripheral angle AMN subtend on AN, that is the diameter of this semicircle, peripheral angle AMN must be equal to 90 degrees in its size according to rule 7. The next step, we define this angle as angle alpha. So in the right angle AMN, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. And 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in this right triangle A and B, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha, according to the sum rule, that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see from the drawing that this is angle A, that is a common angle that belongs to both triangles. Angle A belongs to the right triangle AMN, and angle A also belongs to this right triangle A and B. So angle A is a common angle that belongs to both triangles. In the next step, I'll copy the right triangle AMN and AMB in the new page, and we'll prove that those two right triangles are similar to each other according to angle similarity rule. AM equals to 5 units in its length, according to what is given as the question. AB total equals to x plus A. And the line segment AN, this is line segment AN, that is the diameter of this semicircle. We know that the radius of this semicircle equals to x. Therefore, the diameter must be twice as long as the radius. Therefore, the diameter must be equal to 2x. So AN equals to 2x units in its length. So actually, those are the two right triangles, triangle A and B, triangle A and N, that are copied from the original drawing. So in the next step, we prove that those two right triangles are similar to each other according to angle similarity rule. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. So actually this is angle ABM. In the right triangle A and B, and it is equal to this angle, that is actually angle AMN. In the right triangle AMN. They are both equal to 90 degrees and therefore they are equal to each other. In addition, as I already mentioned, This is angle A, that is a common angle that belongs to both triangles. You can see that angle A also belongs to this triangle A and B. So you can write down that angle A equals to itself as a common angle that belongs to both triangles. So if we write triangle A as it belongs to this right triangle A and B, it will be defined as angle MAB. And angle A equals to itself. So if we write triangle A as it belongs to this triangle, triangle AMN, it will be defined as angle MAN. This equation means that angle A equals to itself. We just call to angle A two different names. So angle A equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So here this is angle A and B. In the right triangle A and B, and it is equal to this angle, that is actually angle A and M. In the right triangle A and M, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we have proved that all the figures of this right triangle A and B are correspondingly equal to all the figures of this right triangle A and N, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. Triangle A and B is similar, this is the sign of similar, to the right triangle A and N according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AM of this right triangle AMN over side AM of this right triangle AMN equals to side AB of this right triangle AMB over side AM of this right triangle AMN. Repeat again. We derive that side AM of the right triangle AMB over side AM of the right triangle AMN equals to side AB of the right triangle AMB over side AM of the right triangle AMN. AM equals to 5 according to what is given as the question. I want to show to you that AM equals to 2x, it is the diameter of the semicircle, and it is equal to AB. AB in total equals to x plus a. Over AM is 5. So in total, according to equation 1, we have found out that 5 over 2x equals to x plus a over 5. Here we cross multiply this equation, equation 1, and finally we get that 5 times 5 is 25, so 25 equals to 2x times x plus a. Here we will divide this equation 1 by 2, and we get that according to this equation 1, 25 over 2 is 12.5, so 12.5 equals to 2x over 2 is x, so in total this expression equals to x times x plus a. So according to equation 1, we have found out that 12.5 equals to x plus x times x plus a. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. And again, the area of a rectangle equals to the length of the rectangle times the width. And therefore, the area of rectangle ABCD must be equal to the length of the rectangle ABCD times the width. The length of this rectangle ABCD is AB, and the width is DA. So in total, we shall find out the area of rectangle ABCD equals to AB times DA. AB in total it is x plus A. DA is x. So in total, we found out the area of rectangle ABCD equals to x plus A times x. But according to equation 2, according to equation 1, x plus A times x equals to 12.5. Therefore, we substitute x plus A times x here by 12.5. So in total, we shall find out that the area of rectangle ABCD equals to 12.5 square units. So actually, in both methods, we found out that the area of this rectangle ABCD is equal to 12.5 square units. So in the next step, I will summarize the lecture. We'll start with the first question, of course. In the first question, our mission is to find out the area of this big circle. So in the drawing, we have those two circles that touch each other at this point C. In addition, we know that this is called AC, that is equal to 6 units in its length. This is called CV, that is equal to 9 units in its length. In addition, we have here tangent DE, that is tangent to this small circle at point B. In addition, tangent DE is tangent to this big circle at this point M. Point B is considered as an external point in relation to this big circle. So from this common external point B, we have tangent BM that is tangent to this big circle at point M. In addition, from the same common external point B, if we draw this straight line, it will cut the big circle at 2 points, A and C. In this way, we get a called AC. So all the requirements of Rule 10 are satisfied, and therefore we can implement Rule 10. According to Rule 10, the following equation will be true, that BM squared equals to BC times BA. Again, BM squared equals to BC times BA. So if it again, according to Rule 10, the following equation is true. BM squared equals to BC times BA. BM is the missing side, so leave it as it is. So BM squared equals to BC. BC is 9 times BA. BA in total equals to 9 plus 16, that is 25. So BM squared equals to BC, that is 9 times BA, that is 25. So in total, BM squared equals to 9 times 25. Here we took out of this equation and found out that BM equals to the square root of 9, that is 3, times the square root of 25, that is 5. So in total, BM equals to 3 times 5, that is 15. Tangent BM equals to 15 units in its length, according to Rule 10. In the next step, we did a construction, that is to say, from this point C, we draw a common tangent that belongs to both circles. And we defined the touching point of the common tangent with tangent DE. This point is point N. Actually, tangent CN is a common tangent that belongs to both circles. Tangent CN is a tangent to this small circle at point C, and tangent CN is also tangent to this big circle at the same point C. Therefore, tangent CN is defined as a common tangent that belongs to both circles. In the next step, we focus on this common sum point N. From this common sum point N, we have two tangents to this small circle, tangent NB and tangent NC. And according to rule 2, they are equal to each other. That is to say, NB equals to NC. According to rule 2. So, in the next step, I copy this triangle C and B in a new page and analyze this triangle C and B. So, okay, this is triangle C and B that I copied from the original drawing. According to rule 2, side CN equals to side NB. In front of this side CN, we have this angle that is alpha. In front of this side NB, we have this angle. So in front of this side CN, we have this angle, that is angle CBN, and in front of this side NB, we have this angle, that is actually angle NCB. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. According to the rule that says that in front of equal sides in the triangle, there are equal angles. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to the rule that I mentioned. So in total, we shall find out that this is angle NCB that is equal to alpha, and this is angle CBN that is also equal to alpha. In the next step, we join points C and M together by a straight line, and we continue to focus on this common sum point N. From this common sum point N, we have two tangents to the big circle, tangent NC and tangent NM. And according to rule 2, they are equal to each other. That is to say, NC equals to NM. So in the next step, I call it right triangle CN. It is not right triangle, I call it triangle CNM in a page, and analyze this triangle CNM. So actually, this is triangle CNM that according to the original drawing, side CN equals to side NM according to rule 2. In front of this side NM, we have this angle NCM. In front of this side CN, we have this angle, that is actually angle CMN. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So if the size of this angle is beta, then the size of this angle must be also equal to beta, because they must be equal to each other according to the rule that I mentioned. So in total, we actually found out that angle MCN, this is angle MCN that is equal to beta, and angle NMC, and angle NMC also equal to beta. In the next step, I copied the big triangle MCB in a new page and analyze this big triangle MCB. So actually, this is the big triangle MCB that I copied from the original drawing. We know that the sum of the angles in any triangle is equal to 180 degrees, and especially it is true in this triangle MCB. So which angles we have? In this triangle MCB, we have this angle that is alpha, plus this angle that is beta, plus this angle that is beta plus alpha. In total, it must be equal to 180 degrees according to the rule that I mentioned. So in this side of the equation, we have alpha plus alpha that is 2 alpha, beta plus beta is 2 beta, so in total 2 alpha plus 2 beta equals to 180 degrees. Here we divided the equation by 2, and finally found out that alpha plus beta equals to 180 degrees over 2 is 90 degrees. So the big angle MCB is the right angle. So this is the big angle MCB, that is the right angle. It is given us the question that AB is a straight line. So if we focus on the left side of the straight line AB at this point C, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of AB at point C? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we join points A and M together by a straight line. AM is a chord inside this big circle. And we have here peripheral angle ACM This is peripheral angle ACM, that is the right angle according to rule 3. And because of the fact that peripheral angle ACM equals to 90 degrees in size, according to rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. And because of the fact that peripheral angle ACM subtend on AM, according to rule 5, AM must be the diameter of this big circle. So in total, we can write down that according to rule 5, chord AM is the diameter of the big circle. We know that the center of any circle must be located on the diameter of the circle. Again, the center of any circle must be located on the diameter of the circle. AM is the diameter of this big circle, and therefore the center of this big circle must be located on AM. This is the center of this big circle that is definitely located on AM. We define the center of this big circle as so. Point O is the center of this big circle, point M is the point of the big circle itself, therefore OM is the radius of this big circle. We define the radius of this big circle as R. And because of the fact that the radius OM that is equal to R, the radius OM is drawn to point M, that is the point of tendency of tangent DE with this big circle, and whenever you have a radius that is drawn to the point of tendency, then tangent DE will be perpendicular to the radius MO. If D is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. The next step, I call it the right big triangle A and B in an page, and implemented the Pythagoras theorem in this right big triangle A and B, triangle A and B. The hypotenuse AB equals to 16 plus 9, that is 25. AM is the missing side, and AB equals to 15 units in strength, according to rule 10. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So this is the right triangle AMN, AMB, that I call it from the original drawing. The hypotenuse AB is 25, AMB is 15, and AM is the missing side. So in this right triangle AMB, AB squared, that is the square of the hypotenuse, equals to AM squared plus MB squared. So we put again, according to the Pythagoras theorem, in the right triangle AMB, AB squared, that is the square of the hypotenuse, equals to AM squared plus MB squared. AB is 25, therefore AB squared is 25 squared, that is 625, and it is equal to AM squared. AM is the missing side, so we leave it as it is, so it is AM squared plus MB squared. MB is 15, therefore MB squared is 15 squared, that is 225. So in total, according to the Pythagoras theorem, in the right triangle AB, 625 equals to AM squared plus 225. Here we subtract 225 from this equation, and finally found out that 625 minus 225 is 400. So 400 equals to AM squared. Here we took a root out of this equation and finally found out that AM equals to the square root of 400, that is 20. So AM equals to 20 units in its length. That means inside AM equals to 20 units in its length. But we already found out that according to rule 5, AM is also the diameter of the big circle. This is called AM, that is the diameter of this big circle according to rule 5. So if the diameter AM of this big circle equals to 20, the radius must be equal to half of it. That is to say, the radius must be equal to 20 over 2, that is 10. So the radius R of this big circle equals to 10 units in its length. And again, the radius R equals to the diameter AM over 2. AM is 20, so 20 over 2 is 10. So in total, the radius of the big circle equals to 10 units in its length. Our mission is to find out the area of this big circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared, and therefore the area of our big circle must be equal to pi times the radius of the big circle squared. The radius of the big circle is 10, therefore the radius squared is 10 squared. So in total, the area of the big circle equals to pi times 10 squared. 10 squared is 100. So in total, this expression equals to 100 pi. 100 pi is 314.159. So in total, we actually found out that the area that we are looking for this question, that is the area of this big circle, equals to either 100 pi square units, so in terms of numbers, the area of this big circle equals to 314.159 square units. we finish with the first question. In the next step, I present to you the second question, and you solve the second question in two different methods. Our mission in this second question is to find out the area of this rectangle ABCD. So in the drawing we have rectangle ABCD, and we also this semicircle. In addition, we know that this is 9:07 a.m. that is equal to 5 minutes in itself. Again, our mission is to find out the area of this rectangle ABCD. So we start with the first method. First of all, because of the fact that ABCD is a rectangle, all those four angles inside rectangle ABCD, again, because of the fact that ABCD is a rectangle, all those four angles inside rectangle ABCD are right angles. We define the center of this semicircle, this point is point O. We define the radius of this semicircle as x. So OA is the radius of the semicircle, that is equal to x units in itself according to our definition. We define the point of tendency of this center DC with this semicircle, this point is point E. We join points O and E together by straight line. Point O is the center of the semicircle, point E is the point of the semicircle itself. Therefore OE is the radius of this semicircle, that is equal to x units in itself according to our definition. Because of the fact that the radius OE that is equal to x, the radius OE is drawn to point E, that is the point of tendency of tangent DC with this semicircle, and whenever you have radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius EO. If this is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So in total, inside quadrilateral DEOA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees, according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral DEOA, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be a rectangle if not a square. So we write to quadrilateral DEOA as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle DEOA, side EO must be equal to the opposite side DA, but EO is x, therefore DA must be also equal to x units in its length. In the next step, we define this line segment OB as A, and we define this line segment MB as B. OM, we join points O and M together by straight line. Point O is the center of the semicircle, point M is the point on the semicircle itself, therefore OM is the radius of this semicircle, that is equal to x. In the next step, I copy the right small triangle OMB in a new page, and we implemented the Pythagoras theorem on this right small triangle OMB. So actually, this is the right triangle OMB that is coming from the original drawing. In this right triangle OMB, MO squared, that is the square of the hypotenuse, equals to MB squared plus BO squared. MO is x, therefore MO squared is x squared, and it is equal to MB squared. MB is B, therefore MB squared is B squared, plus BO squared. BO is A, therefore BO squared is A squared. So in total, according to the Pythagoras theorem, x squared equals to B squared plus A squared. In the next step, I copied the right big triangle A and B in a new page, and we implemented the Pythagoras theorem on this right triangle A and B. The hypotenuse AM equals to 5 units in its length, according to what is given as the equation. MB equals to B, according to our definition. AB in total equals to x plus A. So this is the right triangle A and B that are coming from the original drawing. In this right triangle A and B, AM squared, that is the square of the hypotenuse, must be equal to MB squared plus BA squared. MB is 5, therefore MA, the hypotenuse is MA. MA is 5, therefore MA is 5 squared, that is 25, and it is equal to MB squared. MB is B, therefore MB squared is B squared plus BA squared. BA is x plus A, therefore BA squared is x plus A squared. So in total, according to equation 2, I should find out that 25 equals to B squared plus x plus A squared. So 25 equals to B squared plus x plus A squared. X plus A squared equals to x squared plus A squared plus 2 times x times A. So repeat again. according to equation 2, we should found out that 25 equals to b squared plus x squared plus a squared plus 2 times x times a. So here we have b squared plus a squared, and this side of equation 2. But according to equation 1, we have already found out that b squared plus a squared equals to x squared. Therefore, we can substitute b squared plus a squared in this equation 2 by x squared from equation 1. We did it, and we have found out that 25 equals to b squared plus a squared is x squared, and we have x squared again plus 2 times x times a. So in total we have found out that according to equation 2, 25 equals to x squared plus 2xa. So 25 equals to x squared plus x squared is 2x squared plus 2xa. So in total according to equation 2, we have found out that 25 equals to 2x squared plus 2xa. Here we divided this equation 2 by 2, and finally found out that 25 over 2 is 12.5. 2x squared over 2 is x squared plus 2xa over 2 is xa. So in total according to equation 2, we found out that 12.5 equals to x squared plus x squared plus a squared. So 12.5 equals to, here we took out x as a common factor from those two expressions. So x was taken out as a common factor. What is left from x squared after we took from it x as a common factor? What is left is actually x. What is left from xa after we took from it as x as a common factor? What is left is it is actually a. So in total according to equation 2, we should found out that 12.5 equals to x times x plus a. This is according to equation 2. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually we know that the area of any rectangle equals to the length of the rectangle times the width. And therefore the area of this rectangle ABCD must be equal to the length of the rectangle ABCD times the width. The length of this rectangle ABCD is AB and the width is DA. So in total the area of rectangle ABCD must be equal to AB times DA. AB is x plus a and DA is x. Repeat again. AB is x plus a and DA is x. So in total the area of rectangle ABCD equals to x plus a times x. But according to equation 2, x plus a times x equals to 12.5. Therefore we substitute x plus a times x by 12.5 because it is true according to equation 2. So in total we actually found out that the area of rectangle ABCD equals to 12.5 square meters. We finished with the first method. In the next step, I presented to you how to find out the area of this rectangle ABCD according to the second method. So first of all, because of the fact that ABCD is a rectangle, all those four angles inside rectangle ABCD are right angles. We define the center of this semicircle, this point is point O. We define the radius of this semicircle as x. Therefore, OA is the radius of the semicircle that is equal to x units in length according to our definition. DA equals to x according to the first method, so I'll not repeat on the same explanation. We define this line segment OB as A. We define this point as M. The next step we join points M and N together by straight line. By joining points M and N, we can get the peripherical NMA. This is peripherical NMA, and peripherical NMA subtend on AN, that is the diameter of this semicircle. And according to rule 7, any peripherical that subtend on the diameter of the circle or semicircle must be equal to 90 degrees in its sides. And because of the fact that peripherical NMA subtend on AN, that is the diameter of this semicircle, it must be equal to 90 degrees in its size. So peripherical NMA equals to 90 degrees in its size according to rule 7. In the next step, we define this angle as alpha. So in the right angle AMN, this angle equals to alpha. This angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in this right angle A and B, this angle equals to alpha, this angle equals to 90 degrees, and therefore this circle must be equal to 90 degrees 1 half according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. This is angle A, that is a common angle that belongs to both triangles. It is very easy to see that angle A belongs to this right triangle A and B, and angle A also belongs to the right triangle AMN. So angle A is a common angle that belongs to both triangles. In the next step, I copied the right triangle AMN and the right triangle A and B in a new page, and we proved that those two right triangles are similar to each other according to angle similarity rule. So those are the two right triangles AMN, A and B, and AMN that are coming from the original drawing. AN is the diameter of the semicircle, the radius of the semicircle is x, therefore the diameter must be twice as long as the radius. So the radius must be equal, the diameter must be equal to 2x. So AM equals to 2x, AM equals to 5 minutes in its length according to what is given as the equation. AB in total equals to x plus a. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle A. As I already explained, angle A is a common angle that belongs to both triangles. You can see that angle A also belongs to this triangle, triangle AMN. So we can write down that angle A equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees 1 half, therefore they are equal to each other. So we actually prove that all the angles of this right triangle A and B correspond equal to all the angles of this right triangle AMN. Therefore, those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive the side AM of this right triangle A and B, or side AN of this right triangle AMN is equal to side AB of this right triangle A and B, over side AM of this right triangle AMN. So repeat again. We will derive that side AM of the right triangle A and B over side AN of the right triangle AMN equals to side AB of the right triangle A and B over side AM of the right triangle AMN. AM is 5, AN is 2x, AB is x plus a, and AM is 5. So in total we can find out that according to equation 1, 5 over 2x equals to x plus a over 5. Here we cross multiply this equation 1, and finally found out that 5 times 5 is 25, so 25 equals to 2x times x plus a. Here we divided this equation 1 by 2, so 25 over 2 is 12.5, 2x over 2 is x, so in total this expression equals to x times x plus a. So in total, according to equation 1, we actually found out that 12.5 equals to x times x plus a. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. And therefore, the area of rectangle ABCD must be equal to the length of the rectangle ABCD times the width. The length of this rectangle ABCD equals to is AB, and the width is DA. Repeat again, the length of rectangle ABCD is AB, and the width is DA. So in total, the area of rectangle ABCD must be equal to AB times DA. AB is x plus a, and DA is x. Repeat again, AB is x plus a, and DA is x. So in total, the area of rectangle ABCD must be equal to x plus a times x. But according to this equation 1, x plus a times x equals to 12.5. Therefore, we substitute x plus a times x by 12.5. So in total, we actually found out that the area of rectangle ABCD equals to 12.5 square units. So in both methods, we found out that the area of this rectangle ABCD is equal to 12.5 square units. Okay, thank you very much.